Hello, everyone. Welcome to this Galaxies session that starts the afternoon. I'm Chris Lintott from Oxford. I'm one of your chairs for this afternoon. We'll have time for questions after each talk. And for those online, we'll have somebody monitoring. So if you want to ask questions in the Slack, they'll get passed on. We can just get on with it. So our first speaker is Zsolt Frey from Budapest, and he's talking about large galaxies with Ruben. So over to you.
Thank you very much. I have, I guess, 15 minutes.
Yeah.
So I would like to give you some background about my earlier work so you understand where I'm coming from. This is basically an introduction. And the second half of my talk, I would like to talk about some detailed galaxy classification routines which we have been developing for analyzing these LSST galaxies. I started my work in Princeton as a graduate student with Jim Gunn when they were planning the first three-dimensional real sky survey, SDSS. And that's when we developed the Galaxy Catalog with Ian, which you referred to, I guess, when we got back from lunch. So this was the first real digital galaxy catalog taken with the CCD imagers at Lowell Observatory, at Palomar Observatory, and altogether we had 113 galaxies covering the different Hubble classes. But this was a useful tool because we use this to kind of test and train the morphologic analysis software, which I will describe in the second part of my talk. Now, I just want to tell you that I also participated in Pan-STARRS, and it was a very interesting project since it covered 3 times more sky than SDSS. SDSS had the limitation of covering 1/4 of the sky, 1 pi steradian around the northern galactic pole, avoiding ecliptic. Pan-STARRS was similar to what we are going to do here with LSST. Pan-STARRS wanted to discover transients, actually was financed by the Air Force and trying to look at Earth crossing or Earth threatening asteroids, and therefore it covered everything it could see from Hawaii. And one important contribution to that project was that we, at that time at least, discovered the largest object in the sky, which was a huge void about 220 megaparsecs across, basically a number of about 10,000 galaxies missing in this void. So it was a dip in the average mass distribution. It made the cover of Scientific American because it was an important discovery at that time. I have been working for LIGO since 2007, and one interesting contribution which we keep doing with my students and postdocs in Budapest is developing a galaxy catalog to identify or help identifying sources. So obviously, LIGO is sitting on the ground with 2 perpendicular large arms. That's not something which is pointing to a certain direction. Any direction is possible, or almost any direction is possible for a gravitational wave source. And if it is a binary black hole, you cannot see anything important besides gravitational waves. But if it happens to be a binary neutron star, you expect, and we did actually observe electromagnetic counterparts in 2017. But you have to know where to look. And it's very difficult because the error box is quite large on the sky. And if you try to just scan the error box and look only at galaxies, you go 100 times faster than scanning the entire error box because galaxies roughly cover 1% of the sky. So this is just a density of galaxies in our galaxy catalog, and the bottom two lines, you see the sources we used to put together the catalog. What is important to note here is that before we started this work, LIGO had a galaxy catalog which had about 50,000 galaxies. The current reach till LIGO could actually passively observe a merging neutron star signal, gravitational wave coming from a neutron star signal. To that limit, we have about 5 million galaxies. We, in our catalog, which we call GLADE, Galaxy List for the Advanced Detector Era, this is just a compilation of data from different sources. These are not images, just the data. Some value added like star formation rate and things like that. But we have right now 3 million galaxies. So we are not up to 5 million, but that's one job I hope to actually further with the LSST data. If we cover more parts of the sky and we get interesting galaxy coordinates, which are not in the catalog right now, we can work towards the 5 million limit, which we should reach. So it is just showing you the error patch on the sky in this single event, which we observed in 2017. And some of the follow-up partners observed this event about 10 hours after the gravitational waves came in optical using our Galaxy catalog. And the list we provided from the catalog contain this galaxy as number 14 according to the certain priorities which we gave to this galaxy. I just mentioned for 1 second that we are also developing a fleet of CubeSats, which will have gamma ray detectors. About 12 will be orbiting around the Earth, and gamma rays coming from a merging neutron star could be localized by triangulation immediately and very precisely. Maybe actually useful for some collaboration with LSST as well. And we have launched by now actually 3 prototypes from both the Soyuz and the Falcon 9 launch vehicle, and they are detecting gamma rays perfectly. Now let's switch to the second half of my talk, and let's talk about morphological analysis of galaxies. We developed this many, many years ago, and at the end of the talk, I will show you the current version of our software, which is in Python and ready for LSST. What we are doing with the galaxies is quite interesting. We remove the foreground stars first from the galaxy image. Then, in order to fit the bulge and the disk components, we deproject the galaxy to face and orientation. And then in concentric circles, we sum up the light and create a radial light profile, fit the bulge and the disk components. Let me just switch to the next slide, and you can see this fit here. The thick curve is the actual light profile. This is the bulge, and this is the disk component, and the sum is a thin line which overlaps perfectly the light curve we observed. Then we actually remove the bulge from the image, the fitted bulge, so that we can study the disk better. And this image here in the center shows you the face and orientation galaxy without the bulge in the center. You still can see lots of light coming from the disk, but the majority of the bulge is removed. And then we put the disk into polar coordinates and display this on this graph or picture, which has the polar coordinates from 0 to 360 degrees on the horizontal axis and the logarithmic distance, logarithmic r, measured from the center towards the edge of the disk on the vertical axis. And if you have logarithmic spiral arms, then these show up as straight lines in this theta logar picture. And then you can easily create the so-called autocorrelation image of the upper side, just basically shifting it X and Y directions and multiplying it and summing it together. And then this autocorrelation image has this signal clearly in the direction where the arms are. You calculate the second order image moments of this autocorrelated image, and you can immediately find the opening angle of the arms. And then you can use this direction angle to skew this image to this direction so that the arms are actually showing up vertically. In this skewed image, if you collapse it vertically, then you have a one-dimensional profile across the spiral arms. And then you can Fourier transform this one-dimensional profile, and you can measure how much power is there in the 1 or 2 or 3 or 4 whatever mode there is in the actual galaxy. It shows that this example clearly has 2 arms because the most power is in mode number 2, and it's a bit lopsided because there is a significant power in mode 1 as well. And so I don't want to go into many details, but if the galaxy is well resolved, then we can calculate many other parameters from the image of the disk, which you just, saw basically here and here in polar coordinates, like the flocculency, the strength of the arms, and many others. I just want to jump through the current images, which we did in Python. This is how we measure the silhouettes from different directions of the galaxy to precisely turn it to face-on orientation. This is the modern fit of the bulge and the disk components. This is the fitted synthetic bulge. This is where we remove the bulge. And this is the theta log picture. Then comes the skewed theta log picture, the two-dimensional, actually the one-dimensional profile, and the Fourier transform of that profile to study the spiral structure. I rather save a couple of minutes for questions. Thank you very much.
Thank you. Excellent. Then let's start with questions in the room, if there are some. We'll get a mic to you. Yeah.
You cross-correlate thank you for your talk, first of all. And I'm wondering, when you cross-correlate the signal from a multi-messenger satellite or detector.
So you are switching back to that galaxy catalog.
Yes, I have a question about the galaxy catalog. Do you assume a distance, within which the galaxy can be, or do you take all the galaxies possible?
If I understand correctly your question.
Do you have a limit in distance?
Yes.
Yeah.
So I told you that there is a certain distance, currently about 150 megaparsecs, to which the two LIGO detectors are sensitive to a possible binary neutron star merger. So when I'm speaking about the number of galaxies we need to include in this galaxy catalog, we need to include all possible galaxies up to 150 megaparsecs. And
okay, so this is driven by LIGO. Actually.
Yes, yeah. And this is a growing number. So when I say 5 million, that was an estimate for the previous observing run. And it is not a good estimate for the next observing run because it will be more sensitive and the distance will be larger. But still something which we have to constantly build.
Any other questions? I don't think there are any online. So I've got one, which is your pitch angle fitting.
Yes.
There are many galaxies where a single pitch angle isn't the right solution because you have multiple sets of arms or some merger. What happens in your code when that's true?
Okay, so we actually have several ways of trying to solve this inclination angle. This is how I call it position and inclination angle in the software. And so we can do two things. One is to do an autocorrelation image and try to find out the position angle from that. And then we do whatever I showed here quickly, is the so-called silhouettes from the two directions, the minor axis and the major axis, stretch the silhouette so that we kind of overlap the two and find out the pitch angle from that. It's a difficult job and cannot be correct all the time, I understand.
Yeah. No, for sure. It's about how you fail when you fail. Good. Excellent. We should move on, but let's thank our first speaker again. Our next speaker is online. So Jose, if you could share your screen, you should have permission to do that now. We can see that on stage. You want to go into slide show mode?
Can you see my slides?
We can see your slides, but we can see them with sort of all the stuff around them as well. So I don't know whether you want to go into presentation mode.
Okay.
Yeah, that looks good.
Great. Cool.
I think we can go with that. Good. All right. So our next speaker is Antonio Vasquez Mata from UNAM in Mexico, and they're going to talk about morphological classification of galaxies, pick up where we just left off. So over to you.
All right. Thank you. Thank you for having me here. So yeah, I'm Antonio Vasquez, and I'm going to talk on behalf of the Mexican Incan Galaxies collaboration. And this work was led by Gabriela Aguilar, and unfortunately she cannot be here. But well, I'm going to talk to you about this morphological classification of galaxies through structural and star formation parameters using machine learning. So, well, as everybody knows, morphology of galaxies is very important to study the evolution of galaxies, and this classification has been done for a lot of time based on visual classification mainly, and also using photometric information or non-parametric approaches. Of course, the large amount of data in LSST requires scalability on classification task, and of course, machine learning is the tool that can do this job for us. In the literature, you can find different ways to separate galaxies, and some of them are based on photometrical and structural information that apparently can give us good results, good accuracies to classify galaxies. But unfortunately, when we apply machine learning, most of the works are based directly on images. And well, of course, they give us a good results, but just a few works I found in the literature where the machine learning is applied to identify galaxies or to classify galaxies based on photometry or the structural parameters. Based on this, we try to explore this approach that what could happen if we combine this information. I mean, the photometrical information with the structural information. So in this work, we are using the parametric and non-parametric information related to dynamical properties of galaxies and the spatial as well, and the parameters related to colors and differential parameters related to star formation activity. So to do this, we have this data set that basically is a combination of two very large catalogs. The first one is the Manga Visual Morphology catalog that is based on the Desi Legacy images, and the second is the well-known Nair and Abraham catalog based on Sloan images. We chose these two catalogs because these are very similar. The both of them give us information about the Hubble tides based on visual classification, and these two catalogs although they were created using different kind of images that are consistent with the classification, they are only about 1.5 subtypes of scatter between them, and this is comparable to the error associated to expert classifiers on the same galaxies. The combination of these two catalogs give us a final sample of around 80,000 galaxies after combining and cleaning the catalogs. So these are the general properties of this final catalog. These are the redshift, apparent and absolute magnitude in R1, and the morphological types. So to carry out this work, we recategorize these morphologies into two different samples. The first one is just to find a binary classification into early and late types. And the second is to classify galaxies into 5 different classes. And we associate these morphological types in these 5 different classes. The information we are using are this one. First of all, we have colors that are based on the photometry on Sloan. And the second, we have the structural parameters that are the concentration, symmetry, clumpiness, shape asymmetry, Gini, M20, and the Celsius index. These parameters were estimated by Nevin et al. 2023 on Sloan images. And additionally, we are using also the semi-minor to semi-major axis and the asymmetric gradient that is being proposed by Hernandez Toledo. And we use to this work these 4 different configurations to look and to find if the model could be better using probably photometry more than structural. I mean, this is something we wanted to prove or to try to explore. After looking at different machine learning models, we realized that the XGBoost model gives us the best results. So XGBoost is, in general terms, just a series of decision trees. And the combination of the prediction gives us a final combined prediction that we use for the classification. I mean, I'm not going to enter into details, but if you are interested, we can talk about this later. Here are some of the results that we obtain applying this model. Here we have the confusion matrix for the binary case and for the 5 classes case. And in this table, I show you this configuration that I just mentioned before, based just on color or using just structural information. And either in the binary classification or the 5 class classifications, we found that when we take into account all the information we have, I mean, the photometry plus the structural, we have the better results in all the metrics that we are using. So for the binary classification, we get around, let's say, 87% inaccuracy. That probably could be a bit lower than other words reported more than 90%, like Kanabak in 2021. However, we realized that these words that, based on parameters of photometry, these accuracies are higher because they don't take into account lenticular galaxies. And this probably is the big problem in the binary classification, because these are the galaxies that exactly in the middle between early and late type galaxies. And this is where a lot of error sources could come, right? So I think these results are good because we are considering these galaxies. For the case of 5 class galaxies, for 5 class morphology, these results are similar to those reported by Barkey, because although they don't classify into 5 different classes, but in 3 and 4, the tendency here is very similar. As you can see, it depends on the class. The accuracy, let's say, is different over the confusion matrix. So something we wanted to explore is why we find this result. I mean, the parameters we are using, how they contribute to the classification. And this is something that we explored, that is the SHAP tool, that basically this measures to explain how each feature, or in this case, how much the parameter is contributing to the classification, right? So on the left-hand side, we have this plot that overall give us that the color U minus R, the semi-minor to the semi-major axis ratio, and the concentration are the three main parameters to determine if a galaxy is from one type or another morphological type. If we look into more careful these plots, we divide into different morphological types. And for example, here in the middle, we have the corresponding parameters to determine if a galaxy is an elliptical. And in this case, the semi-minor to semi-major axis ratio and the concentrations are the most important parameters. On the other hand, for the very late type galaxies, we realize that the color, the G minus I and U minus R are the most relevant parameters to determine if a galaxy is a very late type galaxy. So, in conclusion, we realize that the structural parameters are more important to decide if a galaxy is an early type galaxy, and the photometry or the colors are the most important parameters to decide if a galaxy is a very late type galaxy. So based on that, we wanted to explore, well, yes, this is a good result, but we have errors, and where these errors are coming from. So here I present some examples for this kind of errors we find. So all these three galaxies are classified as elliptical galaxies in the data set that we are using. In the first case, our model is giving us prediction to be an elliptical. So this is an agreement, and that's fine. In the second case, the model is saying that this is class 1. That means it's a lenticular galaxy. So looking carefully at this image, one can say, okay, yeah, the model is right. So probably the classification in the original data set could be wrong. So we can have an error probably there. And on the third one, the model is predicting a class 3. That means that it's a late type galaxy. When we see that this could be, I don't know, probably a real elliptical galaxy, but also a dwarf galaxy. So here is where we see some problems. So in general, after doing this kind of analysis for a lot of galaxies, we realize that the main possible error sources are coming from the misclassification on the data set, and also on the discordant galaxies that we find in this data set that are the blue early type galaxies that corresponds to up to 12% probably according to Shawinski and also the red late type galaxies that could be up to 20% according to Bamford. So another important source could be the dose reddening due to inclination effect. So in order to find or to explore if removing these galaxies could improve the model, so we did this and we realized that the model results improve up to 7% in particular classes. So something that we also wanted to explore is, okay, well, before the last, this 7% also means that if we clean the sample, we will have good results, but this is not the case if we have a large amount of data or a large data set that, of course, we don't know the morphology and we wanted to classify galaxies. So we recommend to use also this model, this clean model, if you can remove these galaxies. But this is not going to be the case in most of the cases, right? So probably this is just to give you an example of how the model could improve if we remove these galaxies. And finally, we wanted to also explore this hierarchical approach where, first of all, we divide the sample into early and late type galaxies. And once we have the early type galaxies, we only use the structural parameters to do a subdivision into early and this class, and the late type galaxies, once we have it, we use only the photometrical information to separate into more specific classes. So doing this process, the overall results improve 10%. So again, we say in the paper that if the reader wants to use our code, we recommend to use the general code because it's faster than probably this one and has similar results. So these are my conclusions, and in general, I just wanted to point out that we have good results for the binary and phi-class classifications. We identify more or less the general error sources that, well, unfortunately, these are there in the model, and at the moment, we cannot deal with this. The SHAP analysis also gives us an idea of a good tool to detect outliers in a sample. And something that probably is missing still is that we need to probably retrain this code using information not from Sloan, but now from TP1 probably, or the um, or images deeper than we're using from Sloan. And of course, this code is going to be available for the LSST collaboration through a GitHub repository. So thank you, everybody.
Thank you very much for that excellent talk. Do we have any questions in the room? Or maybe I can start with one. So it's very interesting how much the color dominates your classification when you looked at that SHAP analysis. Have you tried seeing what happens to that analysis if you deprive the model of color altogether, if you don't give it any color information? It would be interesting to see whether it does just as well, but relies on some of the other features, or whether performance is really does get worse.
Yeah, actually, probably I didn't mention this, but yeah, when we include or when we consider only structural parameters, we have about, let's say, 55% of accuracy, right? I mean, I don't have the confusion matrix right here, but of course the accuracy decreases. Yeah.
Yeah, no, it'd be fun though if you took out, like, that's with the color, but then just look at the contribution of the structural parameters, right? But if you gave it only, say, black and white images and no color classification, I think that would be interesting.
Oh yeah, of course, yeah. We haven't checked, but yeah, that would be great.
It's a slightly different use case, but yeah,
Yeah,
anyone
sure.
else? Oh, there's a question online. So, Ronan, if you want to relay the question, that'd be great.
Yeah, this from Charles. Which galaxy type got a 7% improvement, and which type had at least improvement? Was it like 0%? And when did you do your first corrections? Building on Chris's question, are late type more troublesome because of their color variations?
Yeah, that's a good question. Well, now that we have hit the confusion matrix, yeah, once I improve the sample, the accuracy is about 7% better for early type galaxies. Sorry, wait, give me 1 second. The 1.5% is for the early type galaxies, and the 7% improvement is definitely for late type galaxy. But here is also something that we have to take into account, and is this very late type galaxies that the accuracy, at least in the confusion matrix, is very low. And this is because we realized that one of the possibilities is because we don't have that many galaxies in this class. So probably this is another reason apart for exactly what Chris just mentioned as well.
Thank you.
Very good. Thank you very much. We should move on, but let's thank the speaker again. Thank you.
Okay, thank you.
And let's see if I can manage to swap the screen share over
You're doing that
while
mic
still
check?
talking, because I can say very slowly while I do this that our next speaker, who is approaching the stage now, is going to be Eric Tolerant from Space Telescope. And you're mic'd, and that's switched on, so I can hand over to you.
Awesome. Audible in the back, yeah? Very back, awesome. All right, so yeah, I'm gonna talk today about structural parameters that resolve galaxies. So when I first wrote this title, I was like, I'm gonna focus on sort of precursor science. As I started writing the talk, I realized that's not really what's useful for this audience, I think. I instead want to turn it into more of like a methods talk, right? This is a slightly nicer way to put it, but in reality, this talk is all of the things that past Eric really screwed up and wants to communicate to you now so you don't have to make all the same mistakes, right? So this is about how you do resolved star structural parameters, but it's really about how you can do it, because in Rubin, we're just going to have way more data than any one person is ever going to be able to handle. So I want to help you do it much more so than tell you about how I did it. So what are the things I'm actually talking about here? So this is not DP1, this is the DESI Legacy Survey, but it illustrates, I think, what Yao was telling us about this morning, about what some of the things I think are most exciting about what the LSST will find, which is the faint little fuzzy blob right in the middle of this image. So if we zoom in on that, it's a thing that, in the context of the whole survey is just a fuzzy blob, but when you zoom in on it, you realize it's got a bunch of little point sources, right? This to me is immediately like, oh, dwarf galaxy, yay! And probably everyone who's going to be in this session, the very next session in this room, the dwarf galaxy session, was also immediately looks at and says, oh, this is exciting. This is exactly the stuff we're looking for. And I think we're going to find hundreds, maybe thousands of these as the LSST survey goes forward, as indeed Yao pointed out, just not with quite as pretty of a picture as this is showing here. The problem is, just looking at that picture, it's pretty nearby, but you don't know how nearby. And that's actually really important, because if you want to do any of the science Yao or any of the speakers in the next session will be telling us about, you really need to understand the properties of these galaxies, right? How bright they are, what their sizes are, all of that is necessary for interpreting what they're trying to tell us about dark matter, for example. And it's a famous / infamous story that even Hubble himself screwed this up, right? Looked at neat little point sources like this that happen to be varying, and thought that some of them were in fact stars, but they were not stars. They were star clusters, right? So this particular example was showing you because it has Hubble Space Telescope follow-up. And some of those things in the, let's see, I don't know if there's a laser pointer, but whatever. The blue dots in the upper left of this image look like stars, but then as soon as you resolve them, you can see there's fuzzy stuff around them. They're actually star clusters. So the distance you get from that is very different, and it really matters when you're doing any sort of interpretation for these. But the beauty of it is, it's still very clearly a nearby enough dwarf galaxy that we can see individual stars. So that's great, right? That's really valuable. But even with that information, even if you have a distance, you still need to be able to fit all those stars and determine what the structural parameters of the galaxy are, how bright it is, what its size is, what its profile is, because all of those go into any of the galaxy formation or dark matter related science that we actually want to do with these galaxies. So that leads to what the main methods part of this talk is about, which is how you go about doing that. So the first part of the problem here that turns out to be where all the trouble lies is that there's all these other pesky sources. The universe isn't actually just dwarf galaxies for some stupid reason. So we have to worry about all of these contaminating background or foreground sources, and we need to model them if we're going to understand the structural parameters of the galaxies we're interested in. So in a large survey, that's reasonably straightforward in that you have a gigantic survey to model the background on. And you just make sure you make a big circle around your galaxy and you ignore the stuff in the middle. And it's pretty straightforward conceptually, at least. The problem is, for all of these things that are at this distance where they're fuzzy in the big surveys, but really interesting in zoom in surveys from space telescopes, the space telescope field of view is small, right? With the exception of Roman and Euclid, they're basically all tiny little squares that just cover the galaxy. And that's not much space to find background sources. And that turns out to lead to a whole host of problems, which is essentially what the rest of this talk is about. So let's back up a notch then and talk about how you go about doing the structural parameter fit. So what I'm showing you here is sort of should stay away from that mic, I guess. What I'm showing you here is that is a statistical graphical model of how you go about doing this kind of problem. The thing on the left here is the model for the galaxy, right? In this particular case, it's a Sirsic profile. So you have a Sirsic index and a size parameter, and then several other things that are just about where it is in the image and how tilted it is and all of those sorts of things. Simultaneously, then, you have to have some kind of background model. That's a statistical model that can be arbitrarily complicated, but for the purposes of this talk, we're going to think about the very simplest one, which is just a flat uniform background, which then has no free parameters. You take these two surface density profiles, put them together into one combined profile, and all you need then is one parameter that says what fraction of the stars are in the background, what fraction are in the foreground. Conceptually, fairly straightforward. And then you have to fit that to your actual data, which is where a lot of the complexity comes in. And there's a whole lengthy literature on this spanning, this is sort of for the dwarf galaxy community, but it spans many more decades in the past for other communities that have, that are somewhat brighter. Brighter meaning the objects, not necessarily the people. You can decide. So the traditional way this has generally been done is with maximum likelihood. But the more modern approach that is made possible by all the computational capabilities we now have is a Bayesian approach, which is to say you actually build probability distributions over all of those structural parameters. Conceptually, it has a lot in common with the maximum likelihood approach. Ooh. Okay, the equation's a little messed up, but we'll blow past that. The key idea is you have to include some prior on your structural parameters. That part is sort of common to all Bayesian inference approaches. And then for each star, you have to write down a likelihood that says essentially what's the probability of the star is in that spot. And then you treat each star as an individual draw from that surface density, and you multiply them all together. And that's the answer given that particular set of parameters for how likely that parameter value is. You do a bunch of computational magic that the statisticians figured out for us, and bam, you get a nice distribution of structural parameters. One thing I glossed over that in fact turns out to be something you should not gloss over is the fact that that little symbol at the top there is the proportional to symbol, not the equal symbol. For those who are familiar with Bayesian inference, you've probably seen this before. If not, the core idea is just that everything has to be a probability distribution. So you can essentially have a random free normalization parameter that's necessary to make the whole thing integrate to 1, right? That's what all probabilities have to do. They have to add up to 1. So there's always some free normalization parameter. And in most problems we do in astronomy, we throw a whole bunch of stuff into that normalization parameter because we just don't care when we're fitting a bunch of stars that there's 3 stars in the sample instead of 4 or something like that. So you can shove all that in there. That's often safe to do, but it is not safe to do in this case. And the reason why is because it's not just a single simple surface density model, it's this mixture model. So both the background and the foreground have to be modeled separately and normalized separately. And so this is a key thing that is easy to miss when you sort of translate Bayesian literature and Bayesian computational methods into this sort of modeling, that it seems like they can just be freely normalized to whatever they want, but it's the ratio of the background to the foreground that really matters here, so you have to separately normalize each. Now that seems like some weird, subtle mathematical thing that probably doesn't matter that much, but it turns out it completely changes the answer to structural parameters in this small field limit. Yeah, it completely changes the answer because basically the integral you need to do to normalize has to have some outer limit. And in the case where you've got a giant survey and you can draw circles like degrees in the sky, you can essentially integrate to infinity, and that's safe to do because as far as the galaxy is concerned, the outer edge of your survey is infinitely far away. But if you've got a small field of view, either because you did a little cutout from a larger survey or because you're using a space telescope where the field of view is intrinsically small, infinity does not work. It's a much easier to do computationally. It's actually something you can write down and use either your pen and paper or Mathematica to solve, depending on your preference. But it doesn't work for some weird field of view. And to prove that, what I'm showing you here is simulated data, sort of readable from the back, hopefully, where in the middle, what I'm showing you in blue is the distribution of a simulated dwarf galaxy, and in orange, or something like that, which may or may not be visible from the back, is the outcome of what happens when you generate a population based on fitting, assuming the bounds are infinitely far away. And then that fit is what you're seeing on the left is a corner plot of a whole bunch of different probability distributions. And if none of these words really make sense to you, the thing to focus on is the right plot, which is telling you the elliptical, where basically the position angle of the ellipse that's fit. The galaxy itself is supposed to be at 20. And when you do the fit, you get something like 90. The reason why is because the CCD is a rectangle that is aligned with a 90-degree PA. So what it actually is doing is fitting the CCD, not fitting the galaxy, even though that's not super obvious from first glance. And that's entirely due to this effect that you need to consider the bounds when you're in a small field of view. If you do that, if you do sort of some integral transforms, if you do some integral transforms that allow you to do that integral more easily, or just throw a ton of compute power at it, although that's not very efficient, especially at Rubin scale, you can get something that actually turns out much better, that gives you the right position angle, that gives you the right shape parameters, that's basically a perfect match to the generated data when you run it on mock data. But this is not, this is not something that's just like throw it into your maximum likelihood code and it's good. It requires numerical integration of a very subtle type that is not really, you will not find it in NumPy or SciPy or anything. It's something you really have to sort of tie specifically to this problem and this particular surface brightness profile. And just to demonstrate, this does actually work on actual real data as well. So this is some work that Christy McQuinn and Yao Yuan Mao led, identifying things that are little faint fuzzy blobs in the DESI Legacy survey, and then following them up with the Hubble Space Telescope. The image on the left that is really not very good with this projector, but whatever, is supposed to be showing you a dwarf galaxy. I promise it's there in that little circle. So just focus on the circle, and you can see the circle is not aligned to the shape of the CCD, which is essentially the proof that this is actually making a measurement of the galaxy, not of the underlying population of background stars. And the rest, we can blow past that. You can ask me questions about if you want later. All right, then to summarize what I'm hoping you're going to get away from this, it's that Rubin and the LSST will find lots of these sort of barely resolved things where resolved star methods of doing structural parameters are useful, but they're much more useful if you get some space-based follow-up. But if you do that, you have to think about structural parameter fitting differently in the large survey than in the small survey. There's some very important subtleties here that I just went through that you need to worry about and that you need to account for. A corollary to that is like, I haven't seen any discussion of this in the literature on this topic. I would love it if someone would tell me otherwise. I have this feeling like Appendix C to some paper from like 1923 or something went through this in lurid detail, but I haven't seen it yet. So if you've seen it, please tell me, because I don't want to say I invented this if somebody else did it already. And the other thing that I'm asking you all to talk to me about later is if it would be useful for me to turn this into like a nice Python package that you can do, please tell me, because I maintain far too many Python packages and I've gotten to the point where I don't package things up unless I know people are going to use them. So tell me if you want that. Otherwise, I won't take the time to do it. How much time do I have left? Okay, that's actually good. Then one thing that's just, I'm going to call a teaser here, is that the other thing you really want to follow up when we find all these dwarf galaxies in the LSST is you want to get spectroscopic follow-up. And especially for these little fuzzy things that are right at the limit of resolution, you can't really do it from the ground, right? Because they're not well resolved enough from the ground. It turns out JWST near spec is great at exactly that magic point. It's great in the sense that it's well matched to the image quality of JWST, and NearSpec has a multi-object spectrograph that means you can actually get several stars at the same time. What's not great is that it's barely at the resolution you would need to resolve the velocities, the internal velocities of these dwarf galaxies. But with a lot of care and forward modeling and spectral perfectionism, you can actually do it. And if you want to hear more about that, ask me later or in the Q&A. Thanks for your attention.
Thanks, Eric. Good stuff. Does anyone ever say no when you offer to package things up? Do people really say?
It's more whether enough people say
All right,
yes.
fine, good.
Yeah.
Well, there's the challenge for everyone.
Yeah.
Questions? Yeah, Mike coming your way now.
Thanks for the talk.
Yeah.
So I'm asking about whether do you use the fixed size of the background in your analysis, or you find the adequate background size for each object?
Yeah, so this particular model I was showing here doesn't have any assumptions about the background other than that it's uniform over the area of the survey. So there is a size only in the sense of it's the outer bounds of the integral over the background density. So that's that sort of a size scale, but the model itself doesn't have any background size scale.
It doesn't come from the image itself for observations.
It does implicitly through the integral. It's the upper limit of the integral, but the model itself is just that the distribution is uniform within there and there's a sharp cutoff at the edges.
Anyone else? I don't see any online either. Quick one then from me, which is, does this get confounded when you have a particularly clumpy galaxy?
Yeah, good question. So what this model assumes it's just a smooth distribution of stars, which is pretty good for old dwarf galaxies, dwarf spheroidals, if you want to call them that. It would totally fail for like the Magellanic Clouds, which have all kinds of interesting, fascinating, clumpy structure. So then you just have to build a much more complicated model that goes into that left box. But everything else I said is true. It's just the integral is even harder to compute.
Yeah, good. All right, well, let's thank Eric again. Thank you. Our next speaker is online. So Seneca, if you're there, if you can share your screen at this point, that would be fab. Thank you. Good, we can see that coming up now.
Okay, and can you hear me okay?
We can hear you fine. We're just waiting to see your screen. Okay, we can now see if you go into presentation mode.
Okay.
Brilliant. That is working well. So our next speaker is Seneca Barr from Brigham Young, and they're going to talk about an expanded catalogue of galaxies with polar structures. So over to you.
Thanks. Okay, yes, but hello, my name is Seneca Barr. I'm a second-year PhD student at Brigham Young University. I'm very much a newcomer to Rubin and everything that goes with it, so this conference has been a great opportunity for me to learn more about what's out there and what's coming, and it's all really exciting. And today I'm going to share with you a little bit about some ongoing work on an expanded catalog and atlas of galaxies with polar structures, and preparing for the LSST era when it comes to those. So, if it'll let me advance the slide, there we go. I'm going to start off by giving you some background about what is a polar structure galaxy. Basically, anything that fits into this pattern that I have in bold, a galaxy that has two substructures that are separated by a wide angle. Typically, we think like a 90-degree angle. And those structures are therefore photometrically decoupled, and also for a true, what we call a true PSG, they're kinematically decoupled as well. So they're rotating in different directions. Most PSGs follow the pattern of like this little diagram that I have in the bottom left, where there's what we call the host galaxy that is typically redder in color, an elliptical or a lenticular galaxy, and then a bluer polar structure. And I've got a whole bunch of nice examples of different types of polar structures. The most common and the most well-known are polar rings. So you've probably heard something about polar ring galaxies before. Polar structure galaxies are just a broader class of that. And these galaxies, besides, I think, being really beautiful and really interesting just as cool objects that are out there, they're also good laboratories for learning about how galaxies form, how they evolve, the shape of the dark matter halo, and other cosmological questions and things about the Lambda-CDM model, hierarchical galaxy formation, all that sort of interesting things. So to go into a little bit more detail about different types of polar structures, There are a wide variety of types, and in this work, we're just focusing on 4 main ones that are probably the most common and also the most well-defined, easy to define. So that's polar rings and disks, again, the most famous. I have an example of it in the top left corner. The bottom left corner is an example of a polar bulge, so a disk galaxy where the bulge is extended and kinematically decoupled. The top right corner is an example of polar halo, so typically an elliptical galaxy or lenticular galaxy again, where the halo is extended in that polar direction. And then the bottom right is an example of forming polar structures. We see tons of tidal features and arcs and closing, but not quite closed loops in the polar direction. So those are especially interesting, besides being probably the most common out of these 4 categories. They're also great tools for learning about how these galaxies might be forming. And speaking of how they form, there are several proposed formation mechanisms for them. Major mergers are a huge one, as well as tidal accretion, and also cold gas accretion from cosmological filaments. So these have all been discussed in the literature and with models to figure out that they could potentially work. When we're studying these galaxies, there are challenges that we run into, especially with the observations. A lot of these galaxies are quite faint and or have a small angular size because they're quite rare. And so we need to, the percentage of local galaxies that are polar structure galaxies is quite low. So as an example of the difference that deep imaging, deep photometry can make, this is an image of the polar bulge galaxy, UGC 10043. And on the top is from the DESI legacy surveys, and the bottom is from Spitzer infrared image. There's a mask on the top image to kind of help you see the low surface brightness envelope around the galaxy, and especially a little tail in the bottom right corner, and that pops out when you have the really deep imaging. And so because these galaxies are so faint, and a lot of the polar structures themselves are fainter than what we call the host galaxy, it's difficult to identify a large number of these galaxies without deep photometry and without also high resolution photometry for this small angular size. And that's been especially shown last year. There was a paper that came out where they examined the occurrence rate of polar structure galaxies in the Sloan Stripe 82. And using that deep imaging, I think it was almost 4 times the number of galaxies that had originally been seen in that area of sky. And so accounting for the observational effects, we think that although it was previously thought that the occurrence rate of PSGs was about 0.1% of local non-dwarf galaxies, it's actually probably closer to 1%, or if you could correct for all of the inclination angles and everything, up to 3%. So that's really exciting. But it also means that the existing sample that we know of is missing a lot of galaxies. In the literature, there's been, these started being discussed in the 60s, 70s, and there's been a decades-long search for more polar structure galaxies to expand the sample to get better statistics. There's 3 large polar ring catalogs in the literature. When I say large, I mean it contains more than 50 PSGs. And there's many small surveys and papers with discoveries of, 5 new PSGs. And it's very exciting to see them roll out and see the number of these galaxies that we know about increasing over time. So you can kind of see that in the stair step on the left. And a lot of these catalogs include related objects as well. So if you remove out some of the objects that I excluded from this study, such as interpolar disks or gaseous polar structures that you don't actually see in optical photometry, then you end up with about 550 strong candidates for PSGs in the literature, which is a great sample, but like I said, we know that there's more out there. So what I'm talking to you about today is the search to expand that sample. And we started out with the Siena Galaxy Atlas 2020, which uses images from the DESI Legacy surveys, and we use DR9 and DR10. We've paired the images, cropped out all the galaxies, masked to really highlight those low surface brightness features, because a lot of the polar structures are difficult to see without that preparation. And then we went on to the eye classification. So this was combining the efforts of a lot of people, including myself and my advisor and trained undergraduate research assistants. And we went through multiple rounds of checks for each galaxy in this atlas to minimize the amount that we missed. This image is an example of a galaxy classification GUI that was written to help with this. And we also got students involved who were not research assistants, but just students taking the typical second year astronomy class at BYU. They received training, and as part of a class project, they helped with this classification. So that was cool to give them an experience with working with real data on a real science project that was going to go into a publication. And those students actually found about 50% of our final sample, so they made a significant contribution. I'll briefly mention, I won't go into detail, but we also are currently working on a neural network to aid in this classification as well. Since all the eye classification is completed, the point of the neural network is more to find any candidates that we missed. And I put some examples of a few galaxies that the neural network identified as polar structures. And it does have a lot of false positives and it's still in development, but that's another aspect of the project. So going into what came out of it, there's 383,000 galaxies in the Siena Galaxy Atlas. Out of those, we ended up with almost 3,000 polar structure galaxy candidates. I do say candidates because, as I mentioned before, to be called a true polar structure galaxy, the two structures need to be kinematically decoupled, and that's not something that we can confirm with just the photometry as it stands. But a lot of these structures are so distinctive that we feel really good about calling them candidates, and even strong candidates. And if you just do a naive, divide these to get an occurrence rate, you end up with about 0.8% of galaxies in the Siena Galaxy Atlas have polar structures, which is quite close to the estimate from last year of 1% of local galaxies. So that is really exciting and confirms that, yeah, we're finding what we're looking for. We just need that really deep and wide imaging. On the right, I reproduced the plot from earlier and added this work just to give you a sense of how many galaxies this is adding to our sample. The y-axis on the last plot went up to 800, and this one goes up to 3,000, so that's super exciting. Out of the different galaxies that we identified as PSGs, in addition to saying, yes, this is a candidate, there's some type of polar structure, we classified what type of polar structure it appeared to be. So you can see that a little over half of the sample falls into that tidal structures, forming polar rings type of category. And then another quarter is polar rings. That's probably due partly to the fact that there are way more polar rings in the literature already known, which we included in this catalog. And then also just that they're bright and they're easy to recognize at a variety of position angles. So that helps with that. And then the last quarter of the candidates falls into some other main categories: polar bulges, polar halos, and polar dust lanes. Dust lanes in particular, when they're in the polar direction, are often associated with a gaseous polar ring. So that's a way to identify part of the sample that we maybe wouldn't have seen otherwise. And then once we found all these galaxies, we wanted to know a little bit about the population. So we looked at some statistics for the PSGs as compared to the full Siena Galaxy Atlas. So all these plots, I'm going to show you the full Siena Galaxy Atlas is in gray, and the PSG sample is in the orange line. Looking at the right, we can see that the PSGs are somewhat brighter in apparent magnitude. That was pretty expected because it's hard to see something that's dim and hard to identify. But when we change it to absolute magnitude, we see that actually they line up very well with the distribution of magnitudes for the full Siena Galaxy Atlas. So we see polar structures in all different types of galaxies, all morphologies. And then as far as redshift goes, it's kind of similar. They're somewhat overrepresented in the low redshift, but overall line up pretty well. And again, that's pretty expected with it's easier to see things that have less galactic extinction in the way. It's easier to see things that are closer, brighter, bigger, and all of that. And then as well, we looked at the color. So most PSGs are relatively red in color. As I mentioned before, the most common host type of galaxy is lenticular or elliptical galaxies, and the host is often a lot brighter than the polar structure. So this was not totally unexpected. However, there were a non-negligible fraction of polar structures that we found in and around spiral and disk galaxies, late type galaxies. So that was really exciting because that's definitely something that's underrepresented in the literature as it stands. And as far as the color magnitude diagram, again, they're quite aligned with the main sample, a little bit stronger in the redder galaxies. Yeah, so now bring it back to Rubin and LSST. There's a super exciting future for this work as well. And the forthcoming photometry from the survey will be so deep and wide that we'll be able to find even more of these galaxies, increase the statistics even more. Also, the Siena Galaxy Atlas is mostly focused on the northern hemisphere, so having this going on in the southern hemisphere will be really exciting. And then also the capabilities for analyzing low surface brightness features in polar structure galaxies, especially those forming polar structures, and really taking a deep look at those tidal interactions and mergers that we think create these type of galaxies will be super exciting as well. So to sum up, if you haven't heard of PSGs before, now you have. They're really exciting, they're really beautiful, they're really fun to study. They're very rare still, but they're more common than you might think. And the number is increasing all the time due to deep and wide surveys like LSST. And that means that the amount and the quality of the science we can do with these galaxies is only increasing. And I'm really excited about that. Thank you.
Excellent stuff. Thank you for that. Sounds like a really fascinating sample. Questions? There's one online, Moran, if you'd like to relay that for us.
Yeah. Charles says, very interesting. So do you have a high signal to noise spectra for all of your 2993 PSG candidates in the Siena Galaxy Atlas via DESI, I presume, enough for stellar population analysis?
That's a really good question. The answer is no, because a lot of them are quite small galaxies or galaxies that we haven't been able to find spectra for yet, but there is a lot of them do have spectra, and that's something that we're interested in looking into in the future.
Great, thank you. We got one question in the room. While we take that, if the next speaker could start sharing their slides, that'd be great, but we'll take this question.
Thank you very much, Sanika. I have a question for you about the fact that you say that polar structures can be due to both cool accretion and mergers. So is there some properties of the polar structure that you see that will point towards one or the other?
That is a really good question. Not really, but that is something that we're interested in looking into. And I also saw another question online about comparing with simulations, which goes hand in hand with this. So I'm just going to answer both at the same time. That Another aspect of this work that we're planning on doing is comparison with simulations to see if we can identify some of those characteristics that would define the different formation mechanisms or characterize the different formation mechanisms.
Great, thank you. I think that there's at least one more question in the chat for you, but we're going to move on, but maybe you can answer that question there or in the meeting Slack. It's time for our last and definitely not least talk on SED fitting tools, which are going to be essential for what's coming. And giving this talk is Vivek Kumar Jha. So over to you.
I hope I'm audible.
We can hear you and we can see your slide. Yeah, all good.
Oh, thanks. That's great. That's great. Okay, so good afternoon, everyone. My name is Vivek, and I'm going to present the work that we'll be doing as part of our in-kind contribution from NCR TFR. It's we basically are testing different tools for SED fitting, and I'm going to take you to the, just, yeah. Oh, work. Yeah, so Rubin gives us an unprecedented sample size to work with. So we are expecting photometry for about billions of galaxies. And this will enable us to population scale studies of galaxy formation for the first time ever, because we have never had such unprecedented data set so far. And LSST covers a broad wavelength baseline, even though it's optical. So we have 6 bands, which can provide constraints on the stellar population, dust content, star formation history, etc. And there is definitely a need for interpretable physical parameters like stellar masses, star formation rates, and metallicity for such large number of galaxies, which is essential for linking our observations with the theoretical models that we have. And as a result, this will be helpful to advancing the galaxy evolution models, because our assembly of understanding of mass assembly, quenching, and feedback processes will be enhanced by this dataset. And another aspect is this dataset will be foundational for cross-survey synergies, because now we have JWST already, Euclid and SK is coming up soon. So we require a large-scale survey to have cross-wavelength synergies, and in this LSST will be a central part providing the optical filters. So when we say SED modeling, what we do, so here you see that there are different bands of observations that we have, right, from UV to IR. And based on these observations, we model them as a SED, and we get these parameters like masses, transformation rates, metallicity, dust, and all those things in return. So this is basically transforming a physical observations into physical parameters. This technique is called SPS modeling. So there are various tools available. I've listed some of them, and this chart basically tells us that it's a very, very complex thing. You have a lot of parameters going in. You have dust, you have still templates, you have star formation histories, agents there, metallicities, and all these things are there. And different codes have different kind of assumptions, and they have different kind of models to be used. So it's like a very, very complex thing to do. And I've listed some of the codes here. So for our work, we are basically looking at 2 codes to work with. So one is Prospector, there is Bagpipe. So I'm going to show you like what we have been doing so far as part of our contribution. So sorry, slides are not. Oh yeah. So this is our project that is listed on the Galaxies collaboration website, physical properties from Bagpipes and Prospector. And the primary goals that we are trying to address here is these 3. So how consistent are the input parameters between Bagpipes and Prospector? And what are the systematics from the prior choices that we have and the star formation history assumptions? And how much information can we really get from the UGRI-ZY filter sets that we expect from the LSST? So our plan is basically takes 2 different tracks. So one is the large scale SED fitting. So we apply Bagpipes or Prospector to an ensemble of galaxies. We use HSC right now as a test data set, because LSST data, although DP1 is there, but the real LSST data is still to come. So we generate a lot of a catalog of physical properties reaching about millions of sources. Other track is we do interactive high control modeling, where we develop tools so that we can focus on very robust kind of modeling with different kind of priors, with extensive user control over the assumptions of priors and star formation histories and all these things. So right now, prior to LSST, we have a very good data set from the Hypersupreme Camera SSP. So HSP Galaxies, as you can see, I've listed some of the surveys that are going on from HSC, and it provides a very good tested kind of data set before we start working with the real LSST data. We already have 1 million sources to work with, and it gives us a very unprecedented data set to develop and test various algorithms and their scenarios, as well as the limitations of SPS modeling. So as there are multiple surveys there, so we have started with this Galaxy and Mass Assembly Gamma survey. So Gamma is again, it's a very, very large survey which is covering nearby, let's say, 2.5 galaxies. And in the gamma DR3, we have a lot of galaxies which fill in the hypersonic camera ultra deep field. The advantage of survey like gamma is that you have 20 band of photometry available. So, and the other advantage is we have reliable spectroscopic redshifts. So the redshift constraint is already there. So we can use these 20 band photometric data points to constrain the SPS modeling. So yeah, this is the 20 band photometry that we get from the gamma sample for almost all the galaxies that we have. So as we are using the prospector and backpipe, so currently I'll only describe our results with the prospector code that we have found so far. So this is how we model the galaxy with prospector thing. And initially we are using all the 20 filters to put robust controls all these parameters like masses, ages, and velocities. But keep in mind that LSST will be giving only 5 or 6 filters. So the filters that are marked here in the red box here, so these are the only data set that we expect from LSST. So obviously the constraints may not be as accurate as you get from the 20 band filters, but we are testing these kind of hypotheses like how robust we can get. So initially we have run the analysis for about 1500 odd sources from gamma, and this is the distribution you see. So redshift is already constrained. So redshift was not a free parameter during the modeling. And the distribution you see here, we have the masses, metallicities, age, and the dust content. And all these fits they were obtained using prospector. Another advantage of gamma using the gamma sample is that the SPS modeling has already been done using 2 different codes, so it gives us a benchmark to test our analysis. So here we are comparing our the prospector based low stellar masses with the gamma that we have obtained with prospector, and the other one is from prospect, which is already available in the gamma catalog. And you see that our results are slightly they're like slightly deviating from what we expect in prospect. So it's still, it's still work in progress. Star formation history also we are comparing between the prospect and prospector models. And this is again, there is some systematic deviation here that we obtained from prospect. So these
we're
things.
slightly losing you.
Oh, sorry.
I don't know if you can hear me. You might want to turn your video off and see if that helps, because you're breaking up quite a bit.
Oh, I see. Okay. So I have turned my video off. So is the audio better now?
If you're still there, we can't hear you.
Oh,
It might be a little.
It's okay. Hang on a sec. We've just lost we lost the internet in the room for a second. Just give me a second while it comes back.
Okay.
Yeah, Vivek, I can hear you online.
Yeah, he's
Yeah,
clear.
I think it's our end, not you. That should be fine if you pick up from there. Sorry about that.
Yeah, so just let me know which slide did I lose this audio?
I think it was.
Can you hear me?
Yeah.
And we can hear you now.
Okay. So is it fine if I continue from here, or should I go ahead?
Please do that's fine.
Oh, sure. Okay. Yeah. So we were modeling our gamma galaxies with the prospector code, and the redshift was already fixed because we already have the spectroscopic redshift from the gamma catalog itself. So we estimated the stellar masses, metallicities, ages, and then for comparison, because gamma already has a SPS modeling done with the 2 different codes. So we compared our prospector analysis with the prospect code that is already prospect results that are already available. And here I'm showing the comparison between the stellar masses between the 2 codes. So the blue one is our prospector results, and the orange one is the gamma catalog, which is obtained from prospect. And there are some differences between the two, so still it needs to be looked at. And we also compared the star formation histories between the prospector results that we have and with the gamma results that are available from prospect. And as you can see, there is some systematic difference between the two. So still, we are looking at the systematics right now. So now again, we moved into Rubin DP1 also because it came last month, and Rubin DP1 also has extensive coverage across the extended Chandra Deep Field South. So we are trying to see if we can get some photometry from the archive itself. So we found that there is a sample called Music, and this music sample has extensive optical to NIR coverage across the Chandra Deep Field South. So in parallel, we also started to look for SPS modeling for these galaxies. So music has about 11,000 galaxies with photometry across 9 filters in the UV, VRI, Z, JHK, and that will also enable us robust SCD characterization. And the redshift coverage is quite is much better than gamma, so it goes from 0 to up to 1.5. and there are about 8 or 9 filters per source. So the idea is to collect this sample and have a cross match between the music sample and the DP1 and try to see if the Rubin photometry matches many of the sources. And then we try to do SPS modeling on the Rubin DP1 data itself using this catalog. So we have characterized this sample based on the color diagram so far. So here's the two color diagram I'm showing. One is B, R, and RK, and other is the V minus UVJ color diagram, which basically separates the quiescent from the star-forming galaxies. So in this catalog, as you can see, the majority of galaxies are star-forming in the music one. So we are trying to cross-match our galaxies with the Rubin DP1 and try to see if we can get SPS results from this also. Another thing I want to introduce here is this thing called SCD grid. So we're trying to develop an online like SCD viewer which visualizes the large SCD grid population from SPS models. So the idea is to have parameter selection via drop-down menus. So you have like 7 free parameters: age, metallicity, dust, IMF, mass, star formation histories, and the star formation rate. And it supports the partial selection where you can use when you see multiple SCDs, or a full selection where you can see a single SCD curve. And it gives you the option to do a dynamic plotting and interactive exploration for SCDs. And also there is a compact summary panel. It's entirely browser based. So I'll just show you a screenshot. Maybe it will be much more clear there. Yeah. So as you can see, this is a totally browser-based SCD, pre-computed SCD grid. So the idea is you choose the range of parameters that you want to use. And later we will also put an option to put your own photometric data points here. So you overplot your photometric data points and try to generate a pre-computed SCD grid based on your photometric data points, so as to you have some idea about the priors, so that you can set your priors before SCD modeling. So this also might be a bit faster in terms of like zeroing on the priors. So this is like a combination of multiple SCDs that have put here. So as you can see, this spans a wide range of these parameters here. So yeah, the idea is to integrate your own photometric selection here, and you can put your photometric points and just see like where they are lying and which parameters to choose for your SCD modeling. Yeah, so with this, I would like to conclude that LSST ready modeling. So we are using backpacks and prospector to scale well to the large surveys like gamma and music. So it will pave way for the LSST derived data set. Assumptions drive results. So physical parameters vary strongly with the star formation history models and priors. So we need to we need to understand them very clearly, like which models we should use, which priors we should use to benchmark these codes. And music, we are using the gamma and the music survey as a benchmark set. So music will give us 9 photometric points, while gamma gives you 20 photometric points. And they already have secure redshift available. So it enables us to model reliable SPS models and validate the tools between the two. And we are developing a fast browser-based visualization tool, which will across the 7-dimensional model space, which we can use. We can vary all the seven parameters. So it is ideal for intuition, teaching, and maybe prototyping. And the future plans will be to add an AGN, nebular emission, and the photometry uploads and WebAssembly-based interference engine, so that you can try to see interactively like which SAD model will fit your data the best. So with this, I'll conclude. Thank you.
Thank you very much. That was great. And we got all of that minus that little technical hitch in the middle, but everything else came across very clearly. So thank you for that. Are there questions? I have one, which is that for some of the validation data, we're going to have quite patchy coverage of different bands, or we might well have patchy coverage of different bands. Does this sort of work help us understand what we can infer? We don't have full coverage.
I see. I'm just repeating your question just for clarity. So you're asking like for music or gamma, we might not have full 20 band or 9 band coverage, right?
Exactly, and then can
yes.
I was thinking about your interactive tool really to help us understand what we can understand, what we can infer from limited data.
I see. So first I'll just answer this question, this 20 band ones. Yeah, so like you see here, this is the entire 20 band photometry that we collected from gamma. So right now we have done this SPS modeling only for 1500 odd sources. So these 1500, so gamma has like about 200,000 odd sources. So out of 200,000, we selected sources which have secured spectroscopic redshift. So this reduced our sample to about 7,000-8,000. And out of 7,000-8,000, we could find like 2,000 odd sources which have which are all 21 photometry. So right now for validation, we are using only those sources which has the entire photometric dataset coverage. It might bias, but I mean, we are testing the, availability of photometric filters, and we'll try to reduce the filters one by one, and then try to see like what we are losing, what we are gaining, whether we are, losing or not. And the other thing that you're asking about the SED grid. So yeah, so here the idea would be to enable the user to upload a CSV or a text file where you have your own photometric data points, and you try to put your overplot your points on this SED, and you vary all these parameters just to see which points are lying close to your this SED model. So it gives a very intuitive way to set priors before you do the SED modeling. So it might save some computing time as well.
Yeah, no, that's useful. Thank you. Anyone else? Anything online? Good. Well, thank you very much for that talk. Let's thank that speaker again. And in fact, let's thank all the speakers for an excellent and really informative session. I think we'll look back on this in a year's time when we've got the data and we've applied all these techniques and we've got all of our data and realize how important this was. For those online, we're back in the Zoom room in half an hour. If you're staying in the room, we're back here in half an hour for a session on dwarf galaxies of low surface brightness features. But for now, we have a half hour. Bet you have a 33-minute coffee break. So enjoy and catch up with you later in the meeting. Thank you all again.
Thank you. Thanks for coming.